Falcon Heavy. Falcon Heavy, FH, is a super heavy-lift launch vehicle, SHLLV, with partial reusability that can carry cargo into Earth orbit and beyond. It is designed, manufactured, and launched by American aerospace company SpaceX. The rocket consists of a center core on which two Falcon 9 boosters are attached, and a second stage on top of the center core. Falcon Heavy has the second highest payload capacity of any currently operational launch vehicle behind the National Aeronautics and Space Administration's, NASA's, Space Launch System, SLS, and the fourth highest capacity of any rocket to reach orbit, trailing behind the SLS, Energia, and the Saturn V. SpaceX conducted Falcon Heavy's maiden launch on February 6, 2018, at 20:45 Coordinated Universal Time, UTC. As a dummy payload, the rocket carried a Tesla Roadster belonging to SpaceX founder Elon Musk, with a mannequin dubbed Starman in the driver's seat. The second Falcon Heavy launch occurred on April 11, 2019, and all three Falcon booster rockets successfully returned to Earth. The third Falcon Heavy launch successfully occurred on June 25, 2019. Since then, Falcon Heavy has been certified for the National Security Space Launch (NSSL) program. Falcon Heavy was designed to be able to carry humans into space beyond low Earth orbit, LEO, although as of February 2018, SpaceX does not intend to transport people on Falcon Heavy, nor pursue the human rating certification process to transport NASA astronauts. Both Falcon Heavy and Falcon 9 are expected to eventually be superseded by the Starship Super Heavy Lift launch vehicle, currently being developed. Concepts for a Falcon Heavy launch vehicle using three Falcon 1 two-stage small-lift launch vehicle core boosters, with an approximate payload to LEO capacity of 2 tons, 4,400 pounds, were initially discussed as early as 2003 year. The concept for three core booster stages of the company's then as yet unflown Falcon 9 was referred to in 2005 as the Falcon 9 Heavy. SpaceX unveiled the plan for the Falcon Heavy rocket to the public at a Washington, D.C. news conference on April 5, 2011, with an initial test flight expected in 2013. A number of factors delayed the planned maiden flight to 2018, including two anomalies with Falcon 9 launch vehicles, which required all engineering resources to be dedicated to failure analysis, halting flight operations for many months. The integration and structural challenges of combining three Falcon 9 cores were more difficult than expected. On July 19, 2017, Elon Musk said, "It actually ended up being way harder to do Falcon Heavy than we thought. Really way more difficult than we originally thought. We were pretty naive about that." The initial test flight for the first Falcon Heavy rocket lifted off on February 6, 2018, at 20:45 Coordinated Universal Time, carrying its dummy payload, Elon Musk's personal Tesla Roadster, beyond Mars orbit. Musk first mentioned Falcon Heavy in a September 2005 news update, referring to a customer request from 18 months prior. Various solutions using the planned Falcon 5, which was never flown, had been explored, but the only cost-effective, reliable iteration was one that used a 9-engine first stage, the Falcon 9. The Falcon Heavy was developed using private capital, with Musk stating that the cost was more than $500 million. No government financing was provided for its development. The Falcon Heavy rocket design is based on Falcon 9's fuselage and engines. By 2008, SpaceX had been aiming for the first launch of Falcon 9 in 2009, while Falcon 9 Heavy would be in a couple of years. Speaking at the 2008 Mars Society conference, Elon Musk also indicated that he expected a hydrogen-fueled upper stage would follow 2 to 3 years later, which would have been around 2013. By April 2011, the capabilities and performance of the Falcon 9 vehicle were better understood, SpaceX having completed 2 successful demonstration missions to low Earth orbit, one of which included reignition of the second stage engine. At a press conference at the National Press Club in Washington, D.C., on April 5, 2011, Elon Musk stated that Falcon Heavy would carry more payload to orbit or escape velocity than any vehicle in history, apart from the Saturn V moon rocket and Soviet Energia rocket. In the same year, with the expected increase in demand for both variants, SpaceX announced plans to expand manufacturing capacity, as we build towards the capability of producing a Falcon 9 first stage or Falcon Heavy side booster every week and an upper stage every 2 weeks. In 2015, SpaceX announced a number of changes to the Falcon Heavy rocket, worked in parallel to the upgrade of the Falcon 9 version 1.1 launch vehicle. In December 2016, SpaceX released a photo showing the Falcon Heavy interstage at the company headquarters in Hawthorne, California. By May 2013, a new, partly underground test stand was being built at the SpaceX Rocket Development and Test Facility in McGregor, Texas, specifically to test the triple cores and 27 rocket engines of the Falcon Heavy. By May 2017, SpaceX conducted the first static fire test of flight-designed Falcon Heavy center core at the McGregor facility. In July 2017, Musk discussed publicly the challenges of testing a complex launch vehicle like the 3-core Falcon Heavy, indicating that a large extent of the new design is really impossible to test on the ground, and could not be effectively tested independent of actual flight tests. By September 2017, all 3 first-stage cores had completed their static fire tests on the ground test stand. The first Falcon Heavy static fire test was conducted on January 24, 2018. In April 2011, Musk was planning for a first launch of Falcon Heavy from Vandenberg Air Force Base, VAFB, California, on the United States West Coast in 2013. SpaceX refurbished Space Launch Complex 4, SLC-4, at Vandenberg AFB to accommodate Falcon 9 and Heavy rockets. The first launch from the Cape Canaveral, Florida East Coast Launch Complex was planned for late 2013 or 2014. Due partly to the failure of SpaceX CRS-7 in June 2015, SpaceX rescheduled the maiden Falcon Heavy flight in September 2015 to occur no earlier than April 2016. The maiden flight was to be launched from the refurbished Kennedy Space Center, KSC, Launch Complex 39A, LC-39A. The flight was postponed again to late 2016, early 2017, summer 2017, late 2017 and finally to February 2018. At a July 2017 meeting of the International Space Station Research and Development meeting in Washington, D.C., Elon Musk downplayed expectations for the success of the maiden flight. "There's a real good chance the vehicle won't make it to orbit. I hope it makes it far enough away from the pad that it does not cause pad damage. I would consider even that a win, to be honest." In December 2017, Musk tweeted that the dummy payload on the maiden Falcon Heavy launch would be his personal Tesla Roadster playing David Robert Bowie's Space Oddity, though the song actually used for the launch was Life on Mars, and that it would be launched into an orbit around the Sun that will reach the orbit of Mars. He released pictures in the following days. The car had 3 cameras attached to provide epic views. On December 28, 2017, the Falcon Heavy was moved to the launch pad in preparation of a static fire test of all 27 engines, which was expected on January 19, 2018. However, due to the U.S. government partial shutdown that began on January 20, 2018, the testing and launch were further delayed. The static fire test was conducted on January 24, 2018. Musk confirmed via Twitter that the test was good and later announced the rocket would be launched on February 6, 2018. On February 6, 2018, after a delay of over 2 hours due to high winds, Falcon Heavy lifted off at 20:45 Coordinated Universal Time. Its side boosters landed safely on landing zones 1 and 2, LZ-1 and LZ-2, a few minutes later. However, only one of the 3 engines on the center booster that were intended to restart ignited during descent, causing the booster to be destroyed upon impacting the ocean at a speed of over 480 km per hour, 300 miles per hour. Initially, Elon Musk tweeted that the Roadster had overshot its planned heliocentric orbit, and would reach the asteroid belt. Later, observations by telescopes showed that the Roadster would only slightly exceed the orbit of Mars at aphelion. A year after the successful demo flight, SpaceX had signed 5 commercial contracts worth $500 to $750 million, meaning that it had managed to cover the development cost of the rocket. The second flight, and first commercial one, occurred on April 11, 2019, launching Arabsat 6A, with all 3 boosters landing successfully for the first time. The third flight occurred on June 25, 2019, launching the STP-2, U.S. Department of Defense Space Test Program, payload. The payload was composed of 25 small spacecraft. Operational Geostationary Transfer Orbit, GTO, missions for Intelsat SA, formerly Intelsat, and Inmarsat Global Limited, which were planned for late 2017, were moved to the Falcon 9 full-thrust rocket version as it had become powerful enough to lift those heavy payloads in its expendable configuration. In June 2022, the U.S. Space Force, USSF, certified Falcon Heavy for launching its top-secret satellites, with the first such launch being USSF-44, which happened at November 1, 2022, and the second of which being USSF-67, which was launched 11 weeks after USSF-44. Viasat Incorporated, formerly stylized as Viasat, selected the Falcon Heavy in late 2018 for the launch of its Viasat 3, VS3F1, satellite, which was scheduled to launch in the 2020 to 2022 timeframe. However, it would not launch until May 1, 2023. On October 13, 2023, Falcon Heavy embarked on its 8th flight carrying NASA's Psyche probe to the asteroid 16 Psyche. This mission only had the side boosters return to Earth with the center core expended, a decision made to create more tolerable margins for the mission. Following the announcement of NASA's Artemis program of returning humans to the Moon, the Falcon Heavy rocket has been mentioned several times as an alternative to the expensive Space Launch System, SLS, program, but NASA decided to exclusively use SLS to launch the Orion capsule. However, Falcon Heavy will support commercial missions for the Artemis program, since it will be used to transport the Dragon XL spacecraft to the Lunar Gateway, or simply Gateway. It was also selected to launch the first 2 elements of the Lunar Gateway, the Power and Propulsion Element, PPE, and the Habitation and Logistics Outpost, HALO, on a single launch no earlier than 2025, and to launch Astrobotic Technologies' Griffin lander as part of the Artemis program's Commercial Lunar Payload Services, CLPS, initiative. On October 14, 2024, Falcon Heavy transported NASA's Europa Clipper, previously known as Europa Multiple Flyby Mission, into space to explore Jupiter's moon Europa. Falcon Heavy consists of a structurally strengthened Falcon 9 as the core component, with 2 additional Falcon 9 first stages with aerodynamic nose cones mounted outboard serving as strap-on boosters, conceptually similar to the Delta IV Heavy launcher and proposals for the Atlas V Heavy and Russian Angara A5V. This triple first stage carries a standard Falcon 9 second stage, which in turn carries the payload in a fairing. Falcon Heavy has the second highest lift capability of any operational rocket, with a payload of 63,800 kilograms, 140,700 pounds, to low Earth orbit, 26,700 kilograms, 58,900 pounds, to geostationary transfer orbit, GTO, and 16,800 kilograms, 37,000 pounds, to Transmars injection, TMI. The rocket was designed to meet or exceed all current requirements of human rating. The structural safety margins are 40% above flight loads, higher than the 25% margins of other rockets. Falcon Heavy was designed from the outset to carry humans into space, and it would restore the possibility of flying crewed missions to the Moon or Mars. The first stage is powered by 3 Falcon 9 derived cores, each equipped with 9 Merlin 1D engines. The Falcon Heavy has a total sea-level thrust at liftoff of 22.82 meganewtons, 5,130,000 pounds force, from the 27 Merlin 1D engines, while thrust rises to 24.68 meganewtons, 5,550,000 pounds force, as the craft climbs out of the atmosphere. The upper stage is powered by a single Merlin 1D engine modified for vacuum operation, with a thrust of 934 kilonewtons, 210,000 pounds force, an expansion ratio of 117:1 and a nominal burn time of 397 seconds. At launch, the center core throttles to full power for a few seconds for additional thrust, then throttles down. This allows a longer burn time. After the side boosters separate, the center core throttles back up to maximum thrust. For added reliability of restart, the engine has dual redundant pyrophoric igniters, triethylaminium triethylborane, TTEB. The interstage, which connects the upper and lower stage for Falcon 9, is a carbon fiber aluminum core composite structure. Stage separation occurs via reusable separation collets and a pneumatic pusher system. The Falcon 9 tank walls and domes are made from aluminum, lithium alloy. SpaceX uses an all-friction stir-welded tank. The second stage tank of Falcon 9 is simply a shorter version of the first stage tank and uses most of the same tooling, material, and manufacturing techniques. This approach reduces manufacturing costs during vehicle production. All three cores of the Falcon Heavy arrange the engines in a structural form SpaceX calls OctaWeb, aimed at streamlining the manufacturing process, and each core includes 4 extensible landing legs. To control the descent of the boosters and center core through the atmosphere, SpaceX uses 4 retractable grid fins at the top of each of the 3 Falcon 9 boosters, which extend after separation. Immediately after the side boosters separate, 3 engines in each continue to burn for a few seconds in order to control the booster's trajectory safely away from the rocket. The grid fins then deploy as the boosters turn back to Earth, followed by the extending of the landing legs. The side boosters land softly on the ground in fully partially reusable launch configuration. The center core continues to fire until stage separation. In fully reusable launches, its grid fins and legs deploy and the center core touches down on a drone ship. If boosters are to be expended, then the landing legs and grid fins are omitted from the vehicle. The landing legs are made of carbon fiber with an aluminum honeycomb structure. The 4 legs stow along the sides of each core during liftoff and extend outward and down just before landing. The Falcon Heavy rocket uses a 4.5 meters, 15 feet, interstage attached to the first stage core. It is a composite structure consisting of an aluminum honeycomb core surrounded by carbon fiber phase sheet plies. Unlike for Falcon 9 rocket, the black thermal protection layer on the interstage of Block 5 center core boosters is later painted white, as seen in the Falcon Heavy flights so far, probably due to aesthetics of the Falcon Heavy logo, providing it a grayish color. The overall length of the vehicle at launch is 70 meters, 230 feet, and the total fueled mass is 1,420 metric tons, 3,130,000 pounds. Without recovery of any stage, the Falcon Heavy can theoretically inject a 63.8 metric tons, 141,000 pounds, payload into a low Earth orbit, or 16.8 metric tons, 37,000 pounds, to Venus or Mars. However, because of the structural limitations, the maximum weight Falcon Heavy can lift is reduced. The Falcon Heavy rocket includes first-stage recovery systems, to allow SpaceX to return the first-stage boosters to the launch site as well as recover the first-stage core following landing at an autonomous spaceport drone ship, ASDS, barge after completion of primary mission requirements. These systems include 4 deployable landing legs, which are locked against each first-stage tank core during ascent and deploy just prior to touchdown. Excess propellant reserved for Falcon Heavy first-stage recovery operations will be diverted for use on the primary mission objective, if required, ensuring sufficient performance margins for successful missions. The nominal payload capacity to a geostationary transfer orbit, GTO, is 8 metric tons, 18,000 pounds, with recovery of all 3 first-stage cores. The price per launch is $97 million versus 26.7 metric tons, 59,000 pounds, in fully expendable mode. The Falcon Heavy can also inject a 16 metric tons, 35,000 pounds, payload into GTO if only the 2 side boosters are recovered. The partially reusable Falcon Heavy rocket falls into the heavy lift range of launch systems, SHLLV, capable of lifting 20 to 50 metric tons, 44,000 to 110,000 pounds, into low Earth orbit, under the classification system used by a NASA Human Spaceflight Review Panel. A fully expendable Falcon Heavy rocket is in the Super Heavy Lift category, SHLLV, with a maximum payload of 64 metric tons, 141,000 pounds, to LEO. The initial concept, Falcon 9S9 rocket 2005, envisioned payloads of 24.75 metric tons, 54,600 pounds, to low Earth orbit, but by April 2011 this was projected to be up to 53 metric tons, 117,000 pounds, with geostationary transfer orbit payloads up to 12 metric tons, 26,000 pounds. Later reports in 2011 projected higher payloads beyond LEO, including 19 metric tons, 42,000 pounds, to GTO, 16 metric tons, 35,000 pounds, to translunar trajectory, TLI, and 14 metric tons, 31,000 pounds, on a transmartian orbit to Mars, TMI. By late 2013, SpaceX raised the projected GTO payload for Falcon Heavy to 21.2 metric tons, 47,000 pounds. In April 2017, the projected LEO payload for Falcon Heavy was raised from 54.4 to 63.8 metric tons, 120,000 to 141,000 pounds. The maximum payload is achieved when the rocket flies a fully expendable launch profile, not recovering any of the 3 first-stage boosters. With just the core booster expended, and 2 side boosters recovered, Elon Musk estimates the payload penalty to be around 10%, which would still yield over 57 metric tons, 126,000 pounds, of lift capability to LEO. Returning all 3 boosters to the launch site rather than landing them on drone ships would yield about 30 metric tons, 66,000 pounds, of payload to LEO. From 2013 to 2016, SpaceX conducted parallel development of a reusable rocket architecture for Falcon 9, that applies to parts of Falcon Heavy as well. Early on, SpaceX had expressed hopes that all rocket stages would eventually be reusable. SpaceX has since demonstrated routine land and sea recovery of the Falcon 9 first stage, and has successfully recovered multiple payload fairings. In the case of Falcon Heavy, the 2 outer cores separate from the rocket earlier in the flight, and are thus moving at a lower velocity than in a Falcon 9 launch profile. For the first flight of Falcon Heavy, SpaceX had considered attempting to recover the second stage, but did not execute this plan. Falcon Heavy payload performance to geosynchronous transfer orbit is reduced by the reusable technology, but at a much lower price. When recovering all 3 booster cores, GTO payload is 8 metric tons, 18,000 pounds. If only the 2 outside cores are recovered while the center core is expended, GTO payload would be approximately 16 metric tons, 35,000 pounds. As a comparison, the next heaviest contemporary rocket until April 2024, the fully expendable Delta IV Heavy, could deliver 14.2 metric tons, 31,000 pounds, to GTO. Falcon Heavy was originally designed with a propellant cross-feed capability, whereby the center core engines would be supplied with fuel and oxidizer from the 2 side cores until their separation. This approach had previously been proposed by Vladimir Kelemy for the UR-700 launch system. Operating all engines at full thrust from launch, with fuel supplied mainly from the side boosters, would deplete the side boosters sooner, allowing their earlier separation to reduce the mass being accelerated. This would leave most of the center core propellant available after booster separation. Musk stated in 2016 that crossfeed would not be implemented. Instead, the center booster throttles down shortly after liftoff to conserve fuel, and resumes full thrust after the side boosters have separated. At an appearance in May 2004 before the United States Senate Committee on Commerce, Science, and Transportation, Elon Musk testified, long-term plans call for development of a heavy lift product and even a super heavy, if there is customer demand. We expect that each size increase would result in a meaningful decrease in cost per pound to orbit. Ultimately, I believe $500 per pound or less is very achievable. This $1,100 per kilogram, $500 per pound. Goal stated by Musk in 2011 is 35% of the cost of the lowest cost per pound LEO-capable launch system in a 2001 study, the Zenit, a medium-lift launch vehicle that could carry 14 metric tons, 31,000 pounds, into LEO for $35 to $50 million. In 2011, SpaceX stated that the cost of reaching low Earth orbit could be as low as $2,200 per kilogram, $1,000 per pound, if an annual rate of 4 launches can be sustained, and as of 2011 plan to eventually launch as many as 10 Falcon Heavies and 10 Falcon 9s annually. The published prices for Falcon Heavy launches have changed as development progressed, with announced prices for the various versions of Falcon Heavy priced at $80 to $125 million in 2011, $83 to $128 million in 2012, $77 to $135 million in 2013, $85 million for up to 6.4 metric tons, 14,000 pounds. To GTO in 2014, $90 million for up to 8 metric tons, 18,000 pounds, to GTO in 2016. From 2017 to early 2022, the price has been stated at $150 million for 63.8 metric tons, 141,000 pounds, to LEO or 26.7 metric tons, 59,000 pounds, to GTO, fully expendable. This equates to a price of $2,350 per kilogram to LEO and $5,620 per kilogram to GTO. In 2022, the published price for a reusable launch was $97 million. In 2022, NASA contracted with SpaceX Company to launch the Nancy Grace Roman Space Telescope, shortened as the Roman Space Telescope, Roman, or RST, on a Falcon Heavy for approximately $255 million, including launch service and other mission-related costs. The nearest competing U.S. rocket was United Launch Alliance's, ULA's, Delta IV Heavy with a LEO payload capacity of 28.4 metric tons, 63,000 pounds, costs $12,340 per kilogram to LEO and $24,630 per kilogram to GTO. The Delta IV Heavy was retired in 2024. Competitors from 2024 onwards may include Blue Origin's New Glenn, 45 metric tons to LEO, Relativity Space's Terran R, 34 metric tons to LEO, and United Launch Alliance, ULA, Vulcan Centaur, 27 metric tons to LEO. From late 2025 onwards, the SpaceX Starship, 100+ metric tons to LEO, may also be included. Due to improvements to the performance of Falcon 9, some of the heavier satellites flown to GTO, such as Intelsat 35E and Inmarsat 5F4, were launched before the debut of Falcon Heavy. SpaceX anticipated the first commercial Falcon Heavy launch would be 3 to 6 months after a successful maiden flight, but due to delays, the first commercial payload, Arabsat 6A, was successfully launched on April 11, 2019, a year and 2 months after the first flight. SpaceX hoped to have 10 launches every year from 2021 on, but there were no launches in 2020 or 2021. In May 2012, SpaceX announced that Intelsat had signed the first commercial contract for a Falcon Heavy flight. It was not confirmed at the time when the first Intelsat launch would occur, but the agreement had SpaceX delivering satellites to geosynchronous transfer orbit. In August 2016, it emerged that this Intelsat contract had been reassigned to a Falcon 9 full-thrust mission to deliver Intelsat 35E into orbit in the third quarter of 2017. Performance improvements of the Falcon 9 vehicle family since the 2012 announcement, advertising 8.3 metric tons, 18,000 pounds, to GTO for its expendable flight profile, enabled the launch of this 6 metric ton, 13,228 pound, satellite without upgrading to a Falcon Heavy variant. In 2014, Inmarsat booked 3 launches with Falcon Heavy, but due to delays, switched a payload to Ariane 5 for 2017. Similarly to the Intelsat 35E case, another satellite from this contract, Inmarsat 5F4, was switched to a Falcon 9 full-thrust due to the increased liftoff capacity. The remaining contract covered the launch of Inmarsat 6F1 in 2020 on a Falcon 9. In December 2012, SpaceX announced its first Falcon Heavy launch contract with the United States Department of Defense, DoD. The United States Air Force Space and Missile Systems Center awarded SpaceX two Evolved Expendable Launch Vehicle, ELV, class missions, including the Space Test Program 2, STP-2, mission for Falcon Heavy, originally scheduled to be launched in March 2017, to be placed at a near-circular orbit at an altitude of 700 kilometers, 430 miles, with an inclination of 70.0 degrees. In April 2015, SpaceX sent the U.S. Air Force, USAF, an updated letter of intent outlining a certification process for its Falcon Heavy to launch national security satellites. The process included 3 successful flights of the Falcon Heavy, including 2 consecutive successful flights, and the letter stated that Falcon Heavy can be ready to fly national security payloads by 2017. But in July 2017, SpaceX company announced that the first test flight would take place in December 2017, pushing the second launch, Space Test Program 2, to June 2018. In May 2018, on the occasion of the first launch of the Falcon 9 Block 5 variant, a further delay to October 2018 was announced, and the launch was eventually pushed to June 25, 2019. The STP-2 mission used 3 Block 5 cores. SpaceX company was awarded 40% of the launches in Phase 2 of the National Security Space Launch, NSSL, contracts, which includes several launches, a vertical integration facility, and development of a larger fairing, from 2024 to 2027. The payload for the STP-2 mission of the Department of Defense included 25 small spacecraft from the U.S. military, NASA, and research institutions. The Green Propellant Infusion Mission, GPM, was a payload. It is a project partly developed by the U.S. Air Force to demonstrate a less toxic propellant. Another secondary payload is the Miniaturized Deep Space Atomic Clock, DSAC, that is expected to facilitate autonomous navigation. The U.S. Air Force Research Laboratories, AFRL's, Demonstration and Science Experiments, DSX, has a mass of 500 kilograms, 1,100 pounds, and will measure the effects of very low-frequency radio waves on space radiation. The British Orbital Test Bed payload is hosting several commercial and military experiments. Other small satellites included PROX-1, built by the Georgia Institute of Technology, commonly referred to as Georgia Tech, GT, and simply Tech or the Institute, students to test a 3D printed thruster and a miniaturized gyroscope. LightSail by the Planetary Society, Oculus ASR nanosatellite from Michigan Technological University, Michigan Tech, MTU, or simply Tech, and CubeSats from the U.S. Air Force Academy, USAFA, the Naval Postgraduate School, NPS, the United States Naval Research Laboratory, NRL, the University of Texas at Austin, UT, or Texas, California Polytechnic State University, San Luis Obispo, Cal Poly, and a CubeSat assembled by students at Merritt Island High School in Florida. The Falcon 9 Block 5 second stage allowed multiple reignitions to place its many payloads in multiple orbits. The launch was planned to include a 5 metric tons, 11,000 pounds, ballast mass, but the ballast mass was later omitted from the 3.7 metric tons, 8,200 pounds, total mass for the payload stack. In 2011, NASA Ames Research Center, ARC, also known as NASA Ames, proposed a Mars mission called Red Dragon that would use a Falcon Heavy as the launch vehicle and transmartian injection vehicle, and a variant of the Dragon capsule to enter the Martian atmosphere. The proposed science objectives were to detect biosignatures and to drill approximately 1 meter, 3.3 feet, underground, in an effort to sample reservoirs of water ice known to exist under the surface. The mission cost as of 2011 was projected to be less than $425 million, not including the launch cost. SpaceX 2015 estimation was 2,000 to 4,000 kilograms, 4,400 to 8,800 pounds, to the surface of Mars, with a soft retropropulsive landing following a limited atmospheric deceleration using a parachute and heat shield. Beyond the Red Dragon concept, SpaceX was seeing potential for Falcon Heavy rocket and Dragon 2 to carry science payloads across much of the solar system, particularly to Jupiter's moon Europa. However, SpaceX announced in 2017 that propulsive landing for Dragon 2 would not be developed further, and that the capsule would not receive landing legs. Consequently, the Red Dragon missions to Mars were cancelled in favor of Starship, a larger vehicle using a different landing technology. Falcon Heavy rocket is the launch vehicle for the initial modules of the Lunar Gateway, Power and Propulsion Element, PPE, and Habitation and Logistics Outpost, HALO. To decrease complexity, NASA announced in February 2021 that it will launch the first two elements on a single Falcon Heavy launch vehicle, targeting a launch date no earlier than 2025. Before switching to a merged launch, NASA listed in April 2020 Falcon Heavy as the launch vehicle for PPE lone launch. In March 2020, Falcon Heavy won the first award to a resupply mission to the Lunar Gateway, placing a new Dragon XL spacecraft on a translunar injection orbit. NASA chose Falcon Heavy as the launch vehicle for its Psyche mission to a metallic asteroid. It launched on October 13, 2023. The contract was worth $117 million. Europa Clipper was initially targeted to be launched on an SLS launch vehicle. However, due to extensive delays, in 2021 NASA awarded the launch contract to SpaceX for a fully expendable Falcon Heavy. It launched on October 14, 2024. Dragonfly, a rotorcraft mission to Saturn's moon Titan, is scheduled to launch on a Falcon Heavy in July 2028.